Hello everyone. Today in this video clip, I'll continue talking about chapter 16. I'll cover two sections, 16.3 and 16.4. It's about the fundamental theorem for the line integral. And then at 16.4, we're talking about green theorem. Okay? So let's start with 16.3, fundamental theorem for line integral. Let's start with the fundamental theorem of calculus you learned in Cal 1. Cal 1. You have this. The integral of f of x dx run from a to b is going to be equal to big F of b minus big F of a, where the derivative of big F is equal to function f. Okay, so find the antiderivative. Okay, so big F is the antiderivative of small f. Okay, so the fundamental theorem of calculus say what? You integrate a function little f right here. You find the antiderivative. You plug in the upper point, subtract the antiderivative, plug in the lower point. The difference is going to be that value. Okay. So we carry that idea over 16.3 for the line integral. Got a similar idea to antiderivative. Let's write this way then. This is small f is like f right? The integral of the derivative is f2 minus f1, or fb minus fa. Now in Cal 3, the line integral. Okay. Recall we talk about a conservative, right? So if you have the integral of the vector f, let's use the same way as the book do. Remember the line integral of vector field f, okay? And if f is conservative, what do we mean by conservative? I.e., f vector is equal to the gradient of some function f, or some function f. We just talked about that in the previous two section, right? So it only works if the function, the vector field f is conservative. Okay, conservative means that the vector field f, the function vector right here, vector function f, can be expressed as the gradient of some algebra function. Then, if that happens, then this one is the same thing as the integral of the gradient f dr, right? And think of this like derivative. This is gonna be what over this? It's gonna be f right here of the endpoint so I'll say RB minus f of the initial point, right? And C is a curve, okay? It runs from the initial point RA to the endpoint RB, okay? And F is a vector field, okay? Big F right here is a vector field, and it's only true if the vector field F is conservative. It means what? The vector F right here, function, vector function F, can be expressed as the gradient of some other function. Okay. Okay. Say for example from last time, let me just write down. Say I have big F is equal to say 2x comma 1. Okay. Then I claim that this is going to be a conservative vector field because I can find the function f x y equal to x squared plus y, say minus 5. Okay? Because I can calculate the gradient of f. This is equal to df over dx comma df over dy, which is df for dx is 2x, and df of dy is 1, which is f. Okay? So given this, given a vector function f, I can find a two variable function lowercase f equal to this. Actually, it's the constant right here. Is trivial, right? You can choose any constant right here. It will work. I can at least find a function f right here such that the gradient of that function will really equal to the vector function. Then I am safe to say that what this vector field right here is conservative. And if it's conservative, then this thing happens. It's conservative, then the line integral of the vector f dot r right here dr, okay, is dot product to vector. It's gonna be equal to, because f prime is oh, this is from the previous one, because vector f right here is the same thing as the gradient of the function f. So what? It's gradient dot er. It's gonna be satisfy the fundamental theorem of integral or line integral. So what? The endpoint minus initial point, where RB is the endpoint right here, and RA is the initial point right here. Okay. So what does it tell you about this fundamental theorem for line integral? Path independent. It doesn't matter how you go from point A to point B. Okay. As long as the vector field is conservative, doesn't matter which way you go. You're going to have the same answer. Say this is C1, this is C2, C3. Doesn't matter which way you go, as long as you have the same initial point and the same terminal point, then the fundamental theorem for line integral will tell you what. Just take the final, subtract the initial, you have the answer. Okay. Think of in physics rather force, right? It doesn't matter which way you go. If you want to use, you want to carry the same object to point A to point B, it doesn't matter which way you go, you're gonna use the same amount of work. Okay. Now, special case. Now I'm giving you what if f is the conservative already, right? What if the line, the curve C right here is a closed curve? Means what? The initial point and the end point is the same. So you start right here, you go all the way around, and then you go back to the same point. Means what? By theorem, fundamental theorem for line integral, the initial point and the end point are the same. That subtraction will be 0. Okay. And this is actually if and only if. So you have this. This is a theorem say this. If you have the line integral right here in the vector equal to 0 all the time, then you say what? This is independent of path. Or if it's independent of path, then the integral for the closed curve always equal to 0. And the theorem say what? The initial point and the end points are the same. That's why it's 0. Okay. Let me move on and see. Okay, now there's another theorem. Vector field F equal to PQ. Remember, PQ is this is the x component, and this is the y component. There is a function of xy. This is we can tell of xy, right? If F is conservative, then the partial derivative of P out of if y is going to be equal to partial derivative of Q out of x. Why is that? You know that if we have a vector function f conservative, it means what? Vector f is going to be equal to a gradient of some function f, right? Okay? And gradient of some function f is calculated by what? df over dx, comma df over dy, right? Partial derivative of x and partial derivative of y. And this is conservative. So you have this. And this means what? This is your p right here. And this is your q right here. Okay. So far, so good. Now we have a theorem called the Clairaut theorem. Say what? If the function, those functions going to be continuous. Continuous are first order derivatives. It means what? You can take the derivative. Okay. So if this is happened, then you differentiate p in terms of y. dp in terms of dy, and calculate this as well, which is df in terms of dx, and then differentiate in terms of y. d of dy of df over dx. Okay? The derivative of this out of y is dp over dy. And dq over dx, this is q, right? This is d over dx of what? df over dy. Okay? And this is just d squared of f, second derivative, dx, dy. This one is also second derivative of f over dy, dx. And what we learned before, doesn't matter which way you take the derivative first, y first, and this is x first and y second, and this is what? Y first, x second. Those are the same. The same means what? dq over dx is going to be equal to dp over dy. In other words, this is what you want to know. You know that vector field f on 2D is conservative. Then you partial derivative of the first component in terms of y going to be equal to partial derivative of second component in terms of x. Okay. And vice versa. That's a good thing. So if you have this equal, then you know that f is conservative. And this is one way for you guys to check if the vector field f is conservative. So let me give you an example. Okay, how about this? Example, f x y is equal to, how about this? 3 plus 2xy. 3 plus 2xy, comma. Second one is x squared minus 3y squared. X squared minus 3y squared. Let me double check, see if I copy it right. Yes, okay. So this is my p right here, and this is my q right here. A question, is that conservative? So I'm going to check. dp over dy, this is x derivatives of dy, right? So dx dy, right? dy is what? 2x. The second one, dq over dx is 2x. They're the same. And you are safe enough to say what? The vector field f right here is conservative. Because you know it's conservative, and the integral f di is going to be independent of path. And if you integrate on a closed circle and a closed curve, then that's going to be equal to 0. Because we can use the fundamental theorem, right? The initial point and the end point is the same. Integral is going to be 0. Okay, the last thing that's going to be pretty important. Question is, if you are given the vector field f, is there any way for us to find the function f? Question is this, given vector field f conservative. Conservative means what? Means that vector field f is going to be equal to the gradient of some function f. Question, can we find that function f? The answer is yes. So let me give you an example, kind of looking for the entire derivative. Let me show you. Okay. So example, I'm going to give you big F, 2 or 3 variables, 3 variables. Okay. So x, y, z equal to y squared, comma 2xy plus e to the 3z, comma 3y e to 3z, 3y e to the 3z. Okay, so this is my p, this is my q, this is my r. Okay, and I'm telling you what, this f is conservative. So find f. Find f such that gradient of f is equal to big F. So we know that the function f, x, y, z, if you find the gradient of f, so gradient of f is going to be what? df over dx, comma, df over dy, comma, df over dz, right? Partial derivative of f over x is the first component. Partial derivative of f over y, you have second component. Partial derivative of f over z, you have the third component. Okay, and this is really p, and this is q, and this is r. With that much of information, can you find the function f? So let's start with the first one. I got what? df over dx, which is p, which is equal to y squared. So derivative, right? Partial derivative of x equal to y squared. So the function f gotta be of the form f, x, y, z, right? Gotta be of the form what? X, y squared plus a constant. A constant here means what? A function in terms of y and z. Say g of y and z. You see why? Because if this is my function f, then you differentiate it with respect to x partially. Okay, you partial derivative in terms of x, you got what? Y squared, and this, you take the derivative of x, this is like constant for x, so it's 0. Okay, so f, x, y, z gotta be out the form. And now you have to look for that g right here. And I'm done with the first part. Now I'm gonna differentiate function f again, partially with respect to y. So if I got df over dy, I'm moving on to the second term right here, okay? And that's gonna be my q, that's gonna be what? 2xy. And this is my function f. If I differentiate in terms of y, I got what? Sy is 2xy, right? Because differentiate in terms of y, and this is what? Plus dg over dy. Okay? And that's equal to 2xy. Means what? dg over dy is going to be equal to 0. This means dg over dy equal to 0. It means what? This is going to be a function of z only. There's no y in there, because when you take the derivative of y, it's 0. Means what? G is a function of z only. There's no y. Okay? Because z is considered as a constant if you differentiate in terms of y. Okay? So now, with that much information, I can rewrite my function f. F of x, y, z as x, y squared plus gz. I know that there's no y in that function, g right here. Okay? And that's what I get from the second one. From second derivative, df over dy. Now I'm going to move on to the third one. df over dz. Okay? I'm going to integrate this, right? This is what r right here, which is 3y e to the 3z, I think. Oh, did I miss something in here? I wrote something. This one right here. It's not 2xy. Sorry, I missed that. I didn't see that quite. So I have to come back, trace back a little. Sorry, guys, I make a mistake. So let's come back in here. This is equal to not 2xy. It's equal to 2xy plus e to the 3z. Okay? I missed that time. I didn't see that in here. So the dg over dy right here is not 0. So the dg over dy in here is going to be e to the 3z. Okay? And now you can find out the function g in here, yz. You take the derivative in terms of y, it's going to be this, so that one going to be y times e to the 3z, right? Plus a constant. For a constant right here going to be g, so function in terms of z. And right this way. One more time, I apologize, I didn't see the e to the 3z right here. Check it out. if this is your g, y, z, you differentiate with respect to y. Derivative with respect to y, you got what? E to the 3z, right? This is a function in terms of z. Derivative with respect to y is equal to 0. So that's going to be your g of yz. All right. So be very careful with the algebra. Okay. I just didn't see that term, and then I may come to the wrong answer. Lucky that I come back to check because I see this again. So this is my g of yz. I'm going to rewrite my function f right here. I need some room to write. Let me erase that. So my f of x, y, z is going to be xy squared plus g of yz now is what? Y times e to the 3z plus h to the z. With respect to z. This means that the function of one variable z only. Okay, now I gotta use the last one, function with respect to z. So df over dz is gonna be, this is gonna be 0. Df over dz right here, this works, okay? It's gonna be what? 3y e to the 3z, because e to the 3z, derivative in terms of z, chain rules, I've got a 3 in front, plus, this is one what? dh over dz, right? Actually, this is just a prime because one variable. And this is equal to 3y e to the 3z. Last part right here. Now double check the algebra. Should be right. So dh over dz gotta be equal to 0 this time. So h of z gotta be a constant. A constant. Let's write c for constant. Okay. So my final answer for the problem is f of x, y, z gonna be equal to xy squared plus y e to the 3z and plus a constant. And I plan that this is gonna be the function that have the gradient equal to vector function f right here. We want to double check on it. Let's see if it's right. Double check. F of x, y, z equal to x, y squared plus y e to the 3z plus a constant, right? So df over dx, the derivative in terms of x, no x here, no x there, so it's just y squared. Good. First term. df over dy, the derivative of this in terms of y is 2xy. The derivative of the second term in terms of y is going to be e to the 3z. This is constant, the derivative is 0. Yes, second term. Match. Okay? df over dz. Okay, no z here. This one got z, so e to 3z. The derivative got 3 out, so 3y e to the 3z. No z at the end, so that's it. So df over dx, df over dy, df over dz, match up with 3 component p, q, and r. Well, so really, gradient f equal to big F, and you can say that the vector field f is conservative. Okay, for sure. And this is how we find the function f given the conservative. You see, it's not the only function. Okay, it is a family of functions because we have a constant c right here in general. Could be 1, 2, 3, could be any numbers. Okay, and the idea, the strategy to start from the vector field to find the function is what we kind of anti-derivative go backward. We start with the first one, y squared, which is df or dx. We integrate it in terms of x. We have what do we have in there? Xy squared, right? Plus a function in terms of y and z. And then we differentiate that into y, we have q. And then we solve for the part right here. Keep going to the end. Okay? Okay. And then the last part in here, in the book talk about conservation of energy. And up to my knowledge, I think that we have 2 types of energy at least, right? In what potential energy and kinetic energy, but it's pendulum. Remember when I study physics or the spring, we convert from potential energy to kinetic energy up to some point, the highest point. We have maximum potential energy, no kinetic. Pendulum, get to the bottom. You guys go to UCF, you see a long, big pendulum in the math department. And you go to the bottom part, you got maximum kinetic energy, but no potential energy. Doesn't matter what you add the sum of two types of energy together at any point when the pendulum is swinging, the total energy will be a constant, given that no restriction, no friction, nothing. It's just in an ideal condition. That's what happened. And this is conservation of energy. Energy can only convert from one form or one way to another way, but never lose. Okay, let me move on to section 16.4. We'll be talking about green theorems. So far, you have the line integral, you have the conservative field, right? So in green theorem says that if you got the line integral on the closed curve C, okay, vector field F, dr. The only thing in here difference is what? Number one, two things actually. Number one, the curve C will always be a closed curve, simple closed curve. Close. Okay? It means what? The initial point and the end point is the same. We talk about symbol. I think this is not symbol case work too, but we just talk about symbol case in count 3. Symbol closed curve. Okay. And of course, if f is conservative, we learned on the previous section what? That integral will always be 0. Okay? But in this case, more general, what if f is not conservative? Then green theorem say what? This will be equal to integral of dq over dy minus dp over dx. Let me write the same way as the book, right? Make sure that when you guys read the book, you're not going to confuse. Okay. dq, I messed up. dq over dx, dp over dy times dA over the region D, where D is the region inside the symbol closed curve. One more time, the green theorem say what? Instead of integrate the line integral, the boundary of the region, you can convert from line integral back to what? Double integral. Really, this is a double integral, dA, right? Of the region inside the closed curve. And it turns out many times what? The double integral is easier to work with instead of working with the line integral. Of course, you have two ways. If you think that the line integral is easy, then you don't have to use green theorem. You can calculate the answer directly. If it's not easy, another way to do it. And it's only what if the curve is closed and simple. Okay? I don't think symbol is good. It's necessary because I think not symbol works as well. But our book says symbol. Symbol. So we work with symbol closed curve. Okay. And what is P and Q in here? Recall that vector F is written as PQ. Okay? So what? This one is, and R is the equation for the closed curve. So R is x comma y, right? So really, dr is dx, dy. Okay? So this one is no more. This is what I showed you before. Integral pq dot dx dy. Okay, f is pq, and dr is dx dy. On a closed curve C, and this is no more than what? Integral of p dx plus q dy. Okay, so the integral of the line curve C, right? The line integral of the function p respect to x plus the line integral of the function C, of the line of the function q of respect to y. You add them up. It's the same as this one. Okay, this is a short way of writing this, or many books write this way. It's the same. Okay.